Hello, everyone. My name is Sayam Pathak, and you are watching Kubesimplify. And this is a very, very unique, interesting podcast, which is very different from what I have been sharing over past so many years. Because this is not really cloud native thing. This is not really platform infra related thing. This is purely a very different field, but very interesting. It is related to humanoids and it is related to robotics. But it has a very, very big open source angle. And I have a very, very special guest with me today, Ben, who has worked at various big tech companies handling complex problems in Facebook, Tesla, and now he's the CEO of K-Scale. Obviously, we'll dive more into what K-Scale is and what stuff uh, it has for you so that you can get involved as well. But yeah, Ben, thank you so much for joining in today. It would be great if you can just give a quick introduction to the audience.
Yeah, great. Yeah, I'm really excited to talk about what we're doing, especially with developers that are excited to get into humanoids. So I'm Ben. I'm the CEO of K-Scale Labs. Before I started K-Scale, I was an AI researcher at Meta for a while and also spent some time at Tesla on the FSD team. But started K-Scale about a year and a half ago to build the world's best humanoid robot and make it open source and free for anyone to build on top of themselves. That was the mission. What we're doing in K-Scale is building a humanoid robot that any developer can use to get started, trying out the latest ML methods, reinforcement learning methods. We're building an ecosystem on Discord and on Twitter, and just trying to make this as accessible as possible.
Awesome. One of the very cool things that you mentioned is you want to make the ecosystem popular and make it work with the help of community. And that is where the whole open source ecosystem revolves, building a good community so that the project they become successful. And K-Scale, when you go to their website, I'll link everything in the description of the video. It's basically says open source humanoid robots built for developers. So let's start with very, very basic stuff because the audience is pretty new, Ben. So you have to bear with me. So what is a humanoid robot? Like, how do you define on a very in a very high level layman terms what is a humanoid robot?
Yeah. So humanoid robot is just a robot that looks like a human, and it's a good platform for machine learning because a lot of machine learning methods benefit if the robot that you're using looks like a human. But that's pretty technical. Other than that, there's various technical reasons why that's the case, but maybe I can set the stage a bit. So the reason why I left Meta to go start K-Scale was because right now I think we're in the middle of the emergence of the next billion device platform. So, if you look at sort of the history of computing back in the 80s when, when the first personal computers were being explored, I think a lot of people were not sure what a personal computer meant back then. So you can picture yourself, is this a while ago, but basically, computers back then meant, these big mainframe computers that were sitting in, company offices, like they cost hundreds of thousands of dollars. And they were very good at, corporate stuff like, taxes and like maybe financial calculations. Um, and no one really thought of computers as something that you would use in your house to, text message, like message your friend or anything like that. Until the personal computer came out. And I think in the early days of the personal computer, a lot of people were very skeptical that this was something that people would even want. But, if you fast forward a few years, with the internet and the emergence of a few other technologies, suddenly, half the world is, using personal computers and, programmer, like someone that can build apps for personal computers is suddenly like an incredibly valuable job to have. Um, you look forward at the sort of the next big device shift was for, the iPhone. When the iPhone came out, people in the early days of the first iPhone didn't sell more than 1 million units. I might be incorrect. I believe the first iPhone sales were not as big as people might remember, but suddenly there was this idea of like an app developer. So someone could actually go and like make a living by building applications for iPhones. And the emergence of the iPhone was the thing that let, you know, like Instacart or Uber, Facebook even, like a huge number of apps like were built on top of the iPhone. This was something that before iPhones came out, no one could even picture what, an Uber would look like. This is like no one had, phones in their pockets all the time to be able to, just call a car. So this is not a business that anyone thought about. But suddenly this was like, this sort of, because of the right time, like these sort of billion-dollar businesses emerged. And that's why it motivates me to sort of build humanoid robots in the way that we're building it, because I think right now we're in the early days of robots, and everyone that is interested in robotics is sort of wondering what is going to be the next, billion device platform for robotics. Because if you have a billion robots and they're general purpose and easy to program, then maybe, maybe someone will be able to create the next Uber or, DoorDash or Instacart or something like that. Like, there's, and it's going to require a lot more creativity, I think, than people have today, because the people that, like, there's going to be a lot of like a lot of things that will make sense in 4 or 5 years will not really make sense as business ideas today to anyone. That's even like, all of the giants like Facebook, Google, none of those guys will be prepared for what's coming around the corner. And people that are excited and want to get into this field now are going to be the ones that can really take advantage of that. So that's what K-Scale is trying to unlock, is the ability for people who want to start programming general purpose humanoid robots today can get started today. And our goal is to make this timeline happen faster, so that, like the future comes faster.
So that's very interesting. I have a quick question over here. So robots is not a new thing. Robots have been there for a longer period of time doing one particular task which they are good at. We have seen a lot of videos from different organizations where they have, robot picking up a block, robot running, and robot doing a humanoid kind of robot going through a series of obstacles. And those videos have always popped up time and again on our socials and feeds in the news. Uh, what do you think have changed in the past 4 or 5 years? Is it the AI that has picked up in the last 4 or 5 years that you are seeing will accelerate the adoption or the creation of humanoids? What tech technical shifts you are seeing which already have happened or is happening that is making this robotics wave or humanoid wave a lot more crazier than it was maybe 2 3 years ago?
Mm. Yeah. So, um, I think that you should think about humanoids very similarly to how you think about personal computers. So the thing that made personal computers suddenly reach a mass market inflection point was not the software capabilities or the hardware capabilities. It was really the price and the combination of this sort of low-cost platform with a basic set of developer tools and at a price, like basically, and a community and developer ecosystem that could sort of start to snowball this product. I think that humanoids are in the same moment. So, humanoid robots are nothing new. There was a humanoid robot called Asimo from Honda back in the early 2000s. Anybots was another company that built humanoids back then. The difference right now is basically that the price for this humanoid robot is coming down quite a bit. In fact, we're on the verge of seeing a $5,000 full-size humanoid robot, which is something that the world has never seen before. And that's finally in the price point for that's about the price range for the early personal computer. And I suspect it'll come down even more. Our goal at K-Scale really is to try to drive the price down as far as possible, because this is really important for developers. So we have a few different robots. We have a full-size one that's $9,000, a small one that's $1,000, and we're going to have a medium-sized one that's $4,000. It'll all be the same developer ecosystem. But that's really the thing that is exciting to me, is that the price for the humanoid is actually something that, if you're interested in getting into this ecosystem, it's not entirely out of your budget. I mean, it's expensive still, but it's not so expensive that it's unaffordable. Like, it's not $100,000 or $500,000 anymore. So that's the key thing that's happening, and also the machine learning methods. So the reason why low cost hardware is now able to be useful is because actually the machine learning methods are getting much better. So it's actually 20 years ago, if you wanted to make a robot walk, you needed to have like a very powerful, very, very good, like high accuracy actuators. You have very high accuracy IMU. I have an anecdote about this. I was talking to the CEO of Anybots last Thursday, and he told me that their robot IMU costs $2,300 for just the IMU. Our IMU costs 50 cents. And I think, the $2,300 is almost half the cost of the whole robot. So basically, the reason why this is possible today is because now the way that you make a robot walk is you basically build a simulation of that robot, you put it into a simulator. All of this is available on our website, but you put it in the simulator, you can add a lot of noise to the sensors to account for the noise of the low cost, real world sensors. And you train it to achieve some reward function in simulation, over a million different epochs. And then you put that thing onto a real robot, and it just works. So it's a very different approach from what we did 20 years ago.
That is pretty interesting. That cost is coming down. And I think now I am properly getting the story of it mapping, that you map to the personal computers, that they were there for specific tasks similar to that. The robots, which were from 2000 still, 2015, 16 era, for certain tasks, but the costs were high. So basically they were for the enterprises who had the money, but not for the developers who just want to play around, build on top of that, make sure that the algorithms, the ML workflows are running perfectly fine, or they can train them to do certain amount of tasks, has become easier along with all the AI innovation that is happening. And it has led to the cost down by a lot of fractions, which is really, really good. All right. I mean, I think I get a gist of what a humanoid is and why it is important. Now let's get into K-Scale. Explain us about K-Scale, what it is, and what are different components of K-Scale and stuff like that.
Yeah, of course. K-Scale is a company that is democratizing humanoid robot technology. So when I was at Tesla, I actually got to be a part of the early Optimus development. So this was back in 2022. It was, we were the FSD team that I was working on was building a lot of models that were sort of also useful for Optimus perception. And I saw kind of the early signs of this becoming a really big industry. And I felt that it was important for me as an engineer who knows about this kind of technology to help influence the direction in a positive way. in particular, if you look at where we are today with humanoid robots, there's companies like Figure and Tesla and Aptronic, and a number of Chinese companies as well, and they're all building these big closed source robots that are expensive, but they have capabilities that are quite cool, and they're trying to sell these as end products to consumers or businesses. And what this looks like, let's say I'm someone that wants to buy a humanoid robot, is I would just go to Tesla and I would just buy Optimus, and it would come to my house and start cleaning my house, doing my dishes, whatever. Which to me sounds like, at first glance, it sounds pretty cool. Who doesn't want a humanoid robot that can do this stuff for you? But if you imagine what that looks like across the whole of society, like let's say there's 10 million of these things, I actually think it's kind of dystopian to have these robots that are just in your house doing stuff for you and you don't know how they work. I was on the FSD team. I know the kind of data we collected from the cars, and I think the only way for this technology to really reach the 10 million robot scale, or even more, in a way that actually can get buy-in and trust from average people, I strongly believe the only possible way for that to be realized is by building it as an open source project that anyone can contribute to and audit, see what's going on inside, and help improve. On top of that, I think that just if you look at the history of computing, projects that have been built with open source community first approach have just been able to build much faster and better than other projects, with some exceptions. But for example, you're very familiar. Kubernetes is so popular because it's an open source community. It's able to stay at the front of technology, and I think with humanoid robots, this is a very technical field, and it's very important for Kscale to stay at the forefront of this field. And I think the best way for us to do that is to work with developers who are the best in the world and just want to see this technology advance rapidly. Yeah.
Awesome. So I get the mission of Kscale, and I think being open source, you are justifying the scale that we want humanoids to reach. Billions and billions of humanoid robots actually in the house doing the course is something would be possible only if you have them developed, accelerated with the community effort, with a lot of brains rather than being closed source. And yes, open source is game changing for that, which is good. So like I'm on Kscale Labs, and how do anyone they start reading, or they start actually with Kscale, or what is it like? If you can just give us a tour of, or maybe you can share your screen. If you
Yeah, let me share my screen.
Yeah.
I can go through the website.
If you can just give a tour of what components are, hardware, software, what are the different, because I see there is a OS, there is a programming language that you are coming up with soon. A lot of these things would be interesting to hear about.
Yeah. All right. Can you see it?
Yes.
Yeah. So right now there's you can see our robots. We're planning to launch the orders for this in a few weeks. So stay tuned. But this diagram actually gives a pretty good overview of our ML stack. So at the lower level control, we use reinforcement learning, which we train in simulation to train basic policies to stand up, basic control policies. And at a high level, we use basically support vision language action models, VLA models. This is not a policy. It's just a regular model. I need to correct this. But essentially, we feed camera frames from the robot, the actions, which are the positions, velocities, IMU data from the robot, into an end-to-end transformer. That transformer outputs actions, which the robot then takes. It's fed to the lower level controller. All of it's running on top of, we call it KOS, K-scale operating system. It's a Rust-based operating system that we've developed ourselves. So each of these stacks each component of the stack is open source. You can go browse around our GitHub page to see. Broadly speaking, right now, we divide the humanoid robot problem space into two parts: manipulation and locomotion. Manipulation is the ability to manipulate objects, like pick stuff up, put it into a toaster. Locomotion is the ability to walk, move around. Right now, these are two separate problems, but I think that as we move forward, we're going to combine these into the same single model. It's full body local manipulation. So you can see a bit about our stack here. The application layer is the thing that I'm most excited about getting start building, but it's currently the most underdeveloped. The way that we envision this looking is, for most developers, basically you will view yourself as basically programming this VLA model. So if you like basically you have a K-bot, you're like testing it out around your house. You can think of this kind of like stable diffusion, where you're prompting a stable diffusion model to give you better images. And I think a lot of the tricks and tips from getting stable diffusion models to behave well will apply to robotics models as well. The way that we're thinking about building us out as a community is through like an app store, or we want to make it very easy for you to share. Like, let's say you do a fine tune of a VLA model, or like LoRa fine tune, or at some level, like some sort of prompting. This K-lang is our kind of idea around chaining together multiple prompts for VLA models into a sort of program that the robot can execute. That way is sort of a way to bootstrap the VLA model until it's good. We haven't really released much of this stuff. This is on our roadmap, but just wanted to describe our plans there. At the ML layer, this is actually already open source, and you can go check it out. So KSIM is our simulation library for training reinforcement learning policies. We built it on top of Majoko MJX, which is a simulator that is supported by Google DeepMind. You can see just like some sort of training stage. This is the policy as it's learning how to walk. So you can go check this out. It uses proximal policy optimization, actor critic method. It's pretty standard in reinforcement learning, although we're adding support for adversarial motion priors and some of the other stuff that you see for like training, more like using human data to train the robot. This is kind of the idea of adversarial motion priors. You can actually go check out our docs for more information about that stuff. If you go to KSIM, we have this task, and I made an hour-long video about how to use KSIM and get started with it. And the docs, I think, are pretty complete, although sometimes outdated. At the operating system level, the goal for the operating system is basically to make it very easy to go from a policy that you've trained or a VLA model prompt to the real robot. And to do this, we built a lot of this infrastructure in like a K-scale operating system. We have a simulation backend for the K-scale operating system, which lets you try out in simulation the same script that you would use to control the real robot. Everything is in Python. The idea is the entire SDK is in Python, although it talks to the Rust backend over gRPC. The idea there is that Python is the easiest way to get started, and we want to make this as easy as possible. So you don't have to install anything. Like the only thing you install is PyKOS, which is just on PyPy. So you can just go to like pip install PyKOS and get started. You can see this is also entirely open source. There's some examples in this repo here.
Yeah, Ben, we are only able to see one
sorry.
copy.
Sorry, I forgot I was not sharing my screen. It's it's on PyPy pip install PyKOS.
Yeah. Okay.
You can go to our GitHub and see more. Yeah, sorry, let me reshare the docs then, because I think it's cool. Alrighty. Okay, I'll just share my whole screen for now. So you can go to docs.kscale.dev to see our docs. Inside KSim, there's a quick start with a tutorial on how to get started programming policies. And that should be pretty complete. So this is the docs. This is the best starting point. PyKOS is on PyPy here. Pip install PyKOS. You can check out the homepage. This is the documentation, and it's got some examples in KOS Py. All that's open source too. So okay. So KSim is probably the main feature for you to get started with. I'll go into like how the best way to get started with KSim, but before that, I just want to show kind of the different robots that we built. Just a bit of backstory. We started with a 3D printed robot called Stompy. This was back in April last year. This was built in our garage. We made another 3D printed one. This is built for like $10K. I paid for it myself. We made another 3D printed one called Stompy Mini, and then we felt that this was still kind of expensive. This was about $8K. So we decided to make this very small one called ZBot V1, which is $350. You can make it yourself. Again, on the docs.kscale.dev, we have the full CAD model, the build materials, and 3D printing guide, assembly guide on the website. This is like the easiest way to get started if you want to just get started today, because you can make this robot yourself. It's fully open source. We have the sim2real pipeline for this as well. That goal there was to basically make it as accessible to everyone as possible. We made another version of the KBot. This is a sort of first like mass production robot, and another version of the ZBot, which is designed to be the mass production version of our 3D printed robot. We're going to release a new version of the ZBot V3, in a few weeks. This will be just another improvement over this one. Basically, this ZBot V2 is the equivalent of KBot V1 for the ZBot. So we're going to release a ZBot V3, which will just be it'll fix a lot of the issues with this one, and that's the one that we're going to be sort of like mass producing. It'll also be same SDK, same like open source software. And then KBot V2 is the production version of our current KBot robot. And then the last thing is we host hackathons in person in the Bay Area. So if you're in the Bay Area and you're around for a hackathon, we're very happy to host you. So that's our website. But the best way to get started if you're interested in getting started today is basically through this RL training challenge. So I'll walk through what exactly this is. Basically, we wanted to make this like training reinforcement learning policies is kind of difficult, but it really shouldn't be. And our goal is to make training reinforcement learning policies as simple as possible. So that's what this repository is. The easiest way to get started is either through cloning our GitHub template or just opening our Colab. And if you open the Colab, you can just basically run through these different cells, and it'll train a robot to walk. Yeah, so you can just go ahead and like click through these. By default, Colab's on a T4 GPU, which is more than enough for training a decent model. You can just try this yourself. It'll show you a cool visualization at the end with your walking policy. And once you have that, you can send it to me and we will try it on the real robot. So this is the easiest way to get started. There's an accompanying tutorial video. And if you have any questions, I am very happy to answer questions on Discord about this. Um, it's the actual details here are pretty complex. So this abstracts a lot of stuff. You're going to have to understand what probability distributions are, and it helps to have done machine learning before, but it should be pretty tractable. And if you try it yourself and get stuck, we are very happy to help you get unstuck. So yeah, that's what K-Scale has built so far, and we plan to release a few more things in the next few weeks, especially around what the hardware that we're using is, how this is built. So yeah.
So basically, the hardware, one of the hardware that is shown was already open source with the 3D model and stuff. But all the other hardwares, you will also be open sourcing all the stuff that build material and everything.
Yeah, that's correct. I'll just show you where that will live once we've got it up on our GitHub page. We have this KBot. So the 0th bot is the version that we open sourced previously. This is the build guide, operating system, whatnot. And the KBot is the version that we will open source for the full size robot. Although it's just like still in kind of alpha stage. So yeah, if you want to check those out, we'll post updates when we've got it all cleaned up and ready to release.
And you mentioned about the K-lang. So what is that like? How is it different? Is it a new programming language itself, or what exactly you're doing with it?
Yeah, this is a bit. We're probably not going to release this for a few months because we need to do some improvements. But the idea here is that if you're sitting at home and you want to program a humanoid robot, and you don't want to learn how to do all this reinforcement learning stuff, you just want to take a policy that works and try it on your robot, and you don't want to train your own model. You just want to get started. Like, what's the easiest way to get started with a humanoid? And you might have seen these models from companies like Physical Intelligence or NVIDIA, vision language models, vision language action models, VLA models. The way that this works is you just take a sequence of videos and actions from a robot, or so videos and perceptions, and a task that you want the robot to do, and then the model will output actions for the robot to do to achieve that task. The problem is that these VLA models are not very good, and they don't generalize very well. So what K-Scale is building, so K-Scale, we also tried our own VLA models on our own robots. We found that they also were not super good right now, because there's not very much data for these VLA models to actually train on, especially in-domain data from our own robot. So, but it's a cool thing to just try starting out. It's like the easiest way. You can just write some text. The VLA model will try to do it, and it will probably succeed like 10% of the time. The idea of K-lang is that because this model is not very good right now, instead of like sitting and prompting it, we want to build a structured language to be able to compose prompts and handle error cases when the robot messes up, because it's pretty easy to detect if it's messed up. And basically, like at the basic level, this is you can think of the VLA model as a neural interpreter for instructions to like prompt instructions, or sorry, a neural interpreter for K-lang. And K-lang is just a sequence of sort of text instructions for the robot to try, and if the robot fails, like sort of handle error cases from the robot failing. It's a high level. It's we wrote our own lexer and parser for this. It's like a proper language, very simple language. It's not Python. The idea is it's like pretty much just composing text prompts. But yeah, we'll release that in a few months. I think that's going to be the thing that's really going to be the best developer experience. But we need to finish the hardware first to get it to the point that the hardware is pretty stable. we'll test the hardware with people that are like more comfortable using, you know, reinforcement learning techniques to like train policies to do stuff. Once that's more or less ironed out, we'll have our VLA models on top of it. And once the VLA model is kind of just working, we'll then go and we'll like sort of open up Klang after like alpha version of this to try out. Yeah.
Right. So Klang basically improves the developer experience of how you train the
Exactly.
VLA model.
Yeah, you really shouldn't train a VLA model yourself. You should be able to take a pre-trained VLA model and just try it out on the robot as quickly as possible. But basically, Klang is very tied to the VLA model, I suspect. So the language itself will just be the same, but it's very similar to like stable diffusion models, where if you prompt stable diffusion with like there's different stable diffusion versions and LoRa fine tunes, and those will change the way that prompts actually get executed. A very similar idea with the VLA model, where different VLA fine tunes or LoRa's will change how your Klang program will get executed. Yeah.
So you mentioned about the VLA policy. What exactly is this vision language action policy?
Yeah, sure. I mean, this is nothing so mysterious. I can just show you some examples from, you know, say like,
And one follow-up question would be like, so there are diffusion models, and then there are some generic LLMs that we have LLM models.
Sure.
Does these humanoids that you are building, they also will be running an LLM alongside of the vision models, or they are only running specific models? Like how it is structured?
Yeah. So most VLA models are built on top of LLMs plus diffusion. It's both LLM and diffusion models in the same model.
Oh, okay.
If that makes sense. So
Yeah.
I'll just show some videos from the physical intelligence VLA model. This is a robot autonomously emptying the dish, like the washing machine, folding clothes, doing other tasks. This is in the physical intelligence office in San Francisco. So yeah, what this model is doing is basically taking camera feed to each hand and outputting the actions for the robot to do to achieve some task. The task is defined in text. So you can read this paper. This blog post will give you a lot more information. But in terms of how the architecture for this looks, is you have a let me see if they have an architecture diagram. One in the paper here. Yeah, I don't remember if they have an actual architecture diagram, but here we go. Yeah, so basically this pre-trained VLM model, you can see the backbone is a pre-trained LLM, and SIGLIP is a vision encoder, a VIT model. So it's building on top of both LLMs and pre-trained computer vision models. It outputs actions, and these actions are, I believe, like flow matching. Oh yeah, train our flow matching VLA model. So flow matching is a variation of diffusion, which is more principled for doing modeling these ODEs. But yeah, so flow matching, you can think of this as basically just diffusion. This is a pre-trained LLM. This is a pre-trained vision transformer, and they're combined with data that physical intelligence is collected to train this end-to-end VLA model. The way that you actually interact with this is basically by providing it with these images, the sequence of images from the robot, in providing it with this text, fold shirt or some other task that you want the robot to do, and it will output a sequence of actions to achieve that task. So yeah, that's kind of what the developer experience will look like for most people that are trying to build to get humanoid robots to do stuff. Is you will feed camera frames from the camera and the robot's head to this VLA model, the plus a task that you want the robot to do, and it will attempt to do that task using this action expert. And it's likely the case that either you will like fine tune that model on a bunch of very specific data for one task, which is what companies like Dino Robotics have done, and they'll be able to achieve some pretty high accuracy rate on that one task, or you will just sort of try to get it to work on a bunch of different tasks, and it'll achieve probably some middling accuracy rate across all the different tasks. And the idea with K-scale is by building K-lang is a way for us to try out the robot on sort of the long tail of tasks and correct for errors if it's not able to do those tasks successfully. That's a good way for us to sort of get the robot out into the world and as quickly as possible. Does that make sense?
Yes, yes, it makes sense. Can you go back to the architecture that you showed me on the home page of kscale.dev?
Yeah. Yep.
So let's try to understand that a bit more, because now I understand the VLA stuff. Uh, so if you
Yeah.
can, if you see here, so when it says, "Hey Kbot, can you put that bread in the toaster?" So it's a series of images plus the prompt that is going as part of that VLA, which is LLM plus diffusion, and then it defines the actions that it has to take to put that bread in the toaster. So the whole body control policy, is that also a model that is trained only on the body
Oh.
specific task,
Yeah. Yeah.
or what is that?
Okay, so if you look at the other robots that people put VLA models onto, like the physical intelligence demos, most of them were wheel-based robots. So actually, the robot is just when it's turned off, it just will sit there. It's not going to fall over. And then you have the VLA model that actually just runs on the hands and it controls the hands. What But the problem for us is that we have two legs and we need to actually keep the robot balancing, which requires this low level controller that we train with reinforcement learning. So rather than just running the VLA model directly, the way that you would run a VLA model directly on a robot is by it outputs the target XYZ and yaw pitch roll for the hand, plus whether or not the gripper is open or closed. That's what the VLA model will output. And you can do inverse kinematics to go from this target position to the joint angles that the robot needs to output to move the hand to that target position. That's how you run a VLA model on a robot like the physical intelligence robots. In our case, because we actually have a humanoid robot and the robot needs to be able to walk around, we can't we can do inverse kinematics, but we need to also have a second policy that keeps the robot standing up. And you can imagine if you're moving the hands around, it might be harder for the robot to stay standing up. So actually we train the full RL policy so that we have the objective is to stay standing up and move the hands to sort of XYZ yaw pitch roll target position. That's our controller. And so the VLA policy will then feed the XYZ yaw pitch roll target positions to our sort of whole body controller, and that whole body controller will then figure out how to both stand up and move the hands to that target position, and that's how we run the VLA model. So this is a slight difference from the physical intelligence robots or other VLA robots that you've seen, because we need to do this walking robot. But in the end, I think this is just the right way to do robotics. So that's kind of what we're supporting. Yeah. Does that make sense?
Nice. Yes, yes. Now I get the whole picture of how stuff is working in conjunction and where people can come in and contribute, especially the BL piece, and the KSIM, which is something that people can come in and try it out in Google Collab, or try to come in and be part of the actual running on a physical board. So I think that's pretty interesting. So, okay, I get the bit of robotics and demonstrate stuff here. A-scale labs, I think the mission of the idea is pretty clear. Uh, what about the next 5, 10 years? Like, what do you think is happening in this series in the next 5 to 10 years?
Yeah, in the next 5 years, I suspect that humanoid robots will become ubiquitous in daily life for most people. I think it'll start with engineers and developers who are excited to try this technology today, and it'll move into educators, some business applications, sort of diffuse throughout society, starting with early adopters. That's how I think technology adoption happens. So, um, I think it will require some creativity at the beginning to see where these applications will be first. I have talked to a number of people that have bought our robots already, and the kind of stuff that people are interested in using it for is just amazing to me. It's stuff I would not have thought about, and I suspect that there's probably a lot more applications that people are like thinking about on their own, like at home, that are way beyond the scope of stuff that I personally think about. Um, and I'm really excited to see where that, like, I think that's going to be the thing that really like starts to move humanity forward and really push the technological progress forward, is going to be like people just trying out random ideas. And maybe one of them is the next Uber, for humanoids. That's kind of that's where I would say, like, within the next 5 years, there will be something like, Uber for humanoids, some kind of mega app like that.
Wow. And I think your idea of the robot app store is really cool because that way it's pretty simple. Like I can get in my head that someone in the community built did something really cool for one specific task, and you can just install that as part of your own humanoid robot, and that is able to perform that particular task with the proper learned model and fine-tuned model that they have done already.
Yeah, exactly. Like, there's just going to be it's going to be so much better for robotics when there's a bunch of people that have robots, and if I am just sitting in my house with my robot and I train something and I get to do something, and I could just send that to my friend, and he can do it on his robot. That's just such a powerful thing, because that that's where you can start actually seeing people solving each other's problems. And that's what being a developer is, really, at the end of the day. Is I'm a developer. I contribute to open source code. I do this because I like to solve other people's problems, and I like people to use the things that I built. And that's kind of what makes programming beautiful to me, is being able to share it with people and see other people running it. And I'm just so excited for that to happen for robotics. I think that's going to be the thing that really unlocks the next billion robots.
Absolutely, Ben. Thank you so much for joining in. Really glad that this particular thing happened. It's really very interesting area for the next decade or so, and also very evolving area where AI is integrating and taking humanoids and robotics to the next level. So it's the right time to kind of get involved, especially in the ecosystem that you are creating, which is open source from the hardware to the software level. I think it's so interesting that anyone who just want to kind of contribute and they feel, oh, they are in some XYZ remote area, they still can be part of it because that's open source. And that's the beauty of open source, that you can be a part of it anywhere in the world and contribute and shape up the future, what it will look like for the humanoids.
Yeah, totally. Yeah, I'm really excited.
Awesome. Thank you so much, Ben, for your time, and thank you so much for coming on Keep Simplify.
Yeah, thank you. Nice.